Okay, we've talked about the measures of central tendency before, the mean, median, and mode. Now we're going to add to it the measures of dispersion. First of all, quick note, the sample, mean, and sample standard deviation are just going to use normal English letters, X bar in this case, and S, whereas the population standard deviation and mean are going to make use of, those are going to make use of the Greek letters, mu and sigma. Okay, everything we do with the sample is meant to somehow denote the population. In other words, if you recall, X bar in our hope is that it will replicate mu or be similar to mu for the population. So we want to get a sample space of the population. If we've got a bunch of little dots, that's our population. We're going to take a sample of it, and we hope that the statistics on this, the X bar and the S, will be close to the statistics or parameters of the population, mu and sigma. So that's the overarching goal here. First off, measures of dispersion, we've got the standard deviation and the variance. Variance, we're not too concerned about. It is a thing. It shows up in a lot of formulas later in statistics, mostly because standard deviation formulas all have a square root with them. So we've got formula for standard deviation of the sample and of the population. Not too much different. The population is what we'll look at first. And again, it's the average distance from the mean. So you can see we're taking a distance here for each point from the mean. Average means we add them all up. That's what the sigma means. Sigma, or the large sigma here, means to sum. So we're adding up all these distances from the mean. The one unique aspect to it is we're going to square it and then take the square root. That eliminates some issues mathematically in the long term. And then after we add them all up, we're going to divide by the total number of pieces of data, right? Sometimes this N will be denoted, because we're talking about a population, as a capital N, just to make things a little bit different than that of the sample standard deviation. So if you see a capital N in a textbook or when you're Googling things, then that's why. So just be aware of that. Again, a capital N to denote the number of pieces of data in your entire population. So you'll see that sometimes. Okay, population standard deviation makes sense. The sample standard deviation a little bit less so, because here we've got dividing by n minus 1. Now the reason for this, again, the whole point is so that this standard deviation, the S in here, will replicate our sigma of the whole population. Well, it was found after many trials that S, when we were just dividing by an N, was not giving us sigma the majority of the time. It was off by a factor. Thus, the formula was changed to n minus 1 in order to better replicate what sigma actually is. Okay, and that's one of the interesting aspects to statistics, is that things are still changing quite a bit, and a lot of this information is not yet set in stone like you would think the rest of the mathematics is. So it's still a fairly new discipline, and that's what makes it exciting in many ways. Okay. Next up, talking about, or we're getting into probabilities and how much data is in what area of a distribution. If we've got this distribution here, so you can always think of some kind of distribution as a probability distribution. This is a nice pretty one. And for the nice pretty ones, we can use the empirical rule. The empirical rule states that it can only be used with a bell-shaped and symmetric distributions. Okay, so the normal curve, that's what we've discussed so far. This looks a lot like the normal curve, but it doesn't have to be the normal curve. It just has to be a normal-ish curve, essentially, in order to use the empirical rule. But what that states is that within one standard deviation of the mean, so from here to here, 68% of our data would lie in this region. Okay. The nice thing about 68%, if you'll notice, that's just the decimal 0.68. And if the area under the curve, again, if it's a probability distribution, then we're talking about all the possible outcomes. So the area under the curve here, or the area under a probability of all possible outcomes, is 1. Okay, and that is the probability, of x for all random variables, or for all, I shouldn't say that. It's the probability of our sample space. Okay. So the area under the curve is going to be 1, probability of our sample space, meaning that the area here under the curve between 1 standard deviation less than the mean and 1 standard deviation more than the mean, this area is 0.68. And you can see accordingly, 2 standard deviations from the mean, we've got an area of 95%, or 0.95, and at 3 standard deviations, 99.7. So the nice thing about the empirical rule is it gives us a very good description without actually having to do calculations of the probabilities associated with distances from the mean, or rather just where your data is in terms of the magnitude or the amount of data. Chebyshev's rule is helpful because with Chebyshev's rule, it works on any data at all. Okay? So with any data, using Chebyshev's rule, and you can go out to far more than 2 and 3 standard deviations, this states that 75% of the data will be within 2 standard deviations from the mean. Okay? A little bit different from the 95% within 2 standard deviations with the empirical rule, but again, this is pretty data. With Chebyshev's rule, this would work even with uniform probability distributions. If you'll recall, rolling 1 dice, if we were to set up the probability distribution of that, this is the one that we did in class, it would look like this at 1/6. Because the probability of each of those occurring, get a 1, 2, 3, 4, 5, or 6, is all 1/6. So Chebyshev's rule works with even ugly or not exciting probability distributions, in that we could still find the amount of data within a given number of standard deviations from the mean. So that's the use for Chebyshev's rule. This, or Chebyshev's rule, will be most helpful for some of you that are taking the, or some of you that have data that's just not very pretty. Lastly, we've got 3 types of data here. Whoops. Option 1, data we can see, data we can list and see every possibility, every single number. Option 2, data of a finite random variable. Okay, this is like the classwork from last week. And option 3, data of a binomial random variable. Binomial random variable, this is 8.2 in your textbook. Okay, and binomial random variables, well, you can see them listed down here, we'll talk about them. But it deals with Bernoulli trials, which there's only 2 possible outcomes, either a success or failure. First off, with option 2, we see we've got a slightly different calculation for the mean, which is nice. It's just the expected value. So take the probabilities associated with the different random variables and the values of those random variables, add them up, and we'll get the mean. Also, the standard deviation is very similar. For the standard deviation, we're taking the expected value of each variable minus the mean. Okay, of those distances from the mean, squaring them, then we take the square root. So with the standard deviation, that calculation actually gets quite a bit simpler when we're talking about finite random variables. Similarly down here with option 3, we've got different calculations, different formulas for each the mean and the standard deviation. Those can dramatically decrease the amount of time you have to spend on calculating things. Obviously, you're only multiplying some numbers and taking a square root. So these can be very simple. The one thing I want to note here is the use of population mean and population standard deviation. Again, with a finite random variable and a binomial random variable, this data will encompass all the possible outcomes. Okay? Thus, we are talking about population data in each of these senses. Okay? With option 1, data that we can see, that's where we may have a sample, we may not.